So this video is supplement to my quantum mechanics class. Today we're going to talk about what is a photon. In this video, I'm going to show you quickly how this photon works and what is called photon. So photon is a name for light quantum. In quantum mechanics, we quantize objects in different formats. So the name given to the light photon, a light quantum, is called photon. So I make comparisons between classical E&M, which is over here, versus the quantum mechanical behavior of the light photon. So these two are very good comparison. Assuming you learn the classical E&M, electricity magnetism, there the light is described in terms of waves. So waves have the wavelengths you can see here, and of course it has frequencies. Now in quantum mechanics, we quantize the light wave in terms of these particles. So the little dots here representing the photons. And nowadays we can detect single photons with a single photon detector like this on the right. The size of photon is dependent on how large the wavelength that is. Usually it's considered as the wavelength is the size of the photon. This concept is really elementary in many ways because it does not discuss the fact that the photon wave may spread around it. But at the minimum order, which we are discussing for the moment, we still use this wavelength as the size of the photon. Let me compare the energy between the E&M and light photon. E&M, the wavelight, the light wave itself has the energy 1/2 c speed of light, epsilon 0 permittivity, and E sub F referring to electrical field because I use another E over here. If we equal these two together, and then we found out the electric field for a single photon is extremely weak, so 10 to the -7. And usually if you have a light come over, if you put a lot of filter in a way, and then the wavelength is going to be, the number of photons is going to be reduced. Just single photon is possible. Just make things weaker as you can. So this is always a way to understand this. Now what's the difference between the diffractions in between the E&M and quantum? E&M, when we have a light source, let's call it S here, and if the slit size on the comparable level of the wavelengths, and then we see the diffraction pattern behind on the screen. So that's just like this. I could not draw very well, but that's what you can see there. In quantum, we can just use single photon, and with this comparable, the slits like this. And this probably, when you shoot the light photon to the slit, and end up maybe in the middle. Now this location itself may be slightly so-called controlled randomness. It's not perfectly random because if you have many more photons, it's going to pile up like this. So this will be considered the classical analog between the quantum and classical way doing that. So the difference between these two, as you can see clearly, single photon is just one single dot on the screen. It does not show you the entire interference pattern, but if you have many more photon comes out and the patterns formed. So this is the distinctive the properties from the classical E&M. Now you may wonder, why didn't I use interference as example? Well, if we use interference, and the difference between E&M and quantum is much less dramatic because there you're going to use two a slit like there, and here I also use 2 slits like that. So at the minimum, you need 2 photons. So so the difference between these two not that obvious or not that dramatic, as I just once mentioned. So number 4, why did Dirac say the photon interferes with itself? In Dirac's quantum mechanics book you will read, Dirac did mention the photon interferes with itself. Because the single photon, if we're sending many more, it will create a pattern just like an interference pattern. The reason was that the single photon itself, even though when we just shoot one, you cannot see the single interference, but in order to see the interference pattern, you didn't need more. So there's an irony between these two. In other words, in order to see the interference, you need more photons. Single photon itself does not manifest it that it has interference, but if you have more, and that effect will comes out. Number 5, what is the photon entanglement? How do we detect experimentally? Photon entanglement means if we create a pair of photons that are entangled from the beginning, they will keep entangled regardless how far apart they are, where they will always remain entangled. This means if you measure one photon, the another photon will be affected. How far that doesn't matter. So regardless how far that is. So this is called entanglement. For instance, if I have a photon 1 and photon 2 create at the same time, even let's say photon 1 go to the right, photon 2 go to the left. These two are entangled. If I measure the photon 1 on the right, it will affect the results on the photon number 2. Regardless how far these two particles are far apart. It's very difficult entanglement. It's kind of difficult to understand it because it just shows you it's non-local. So that's the key concept of John S. Bell's inequality equation. So that is the key idea. So we normally use the coincidence experiment. So you will see in our chapter 1, you're going to see this example. And you may wonder, what is missing from experiment? Well, most experiments use the coincidence as a way to observe the entanglement. One may object this experiment. Typically, when a purist would ask an experiment to show if I manipulate one photon and another photon, you detect also change its quantum state. But this is never done. So that is as always a puzzle involved. So I'm going to stop over here and I'm going to discuss another topic next time. So I won't take you too much time on that.